on morphology for morphological phylogeny for the Hawaiian honeycreepers. She focuses on osteology, so you need to know what that term means, which is basically just the study of bones. So in this paper, you're not going to read the whole thing, so don't panic. You already know a good bit about the honeycreepers and phylogenetics now, so a lot of this should be familiar and should be an easier read. You just want to keep your mind active. What are the things in here that ring true with what we've read in other places? What things are different? And I mean both in terms of honeycreeper evolution and in terms of phylogenetics. So write down in your notes these kinds of comments and questions, and we can use those in your groups on Monday. Our goal in reading this paper is similar to what we did with the owls. We want to compare phylogenetic hypotheses from different data sources. Are the molecular and morphological hypotheses for the honeycreepers similar? How is it different? In what ways and why? And so we'll use insights from the owl work that you did and from the honeycreepers to inform our knowledge of phylogenetics. So it's not just the evolutionary history of these groups, but how does phylogenetics work? How do you develop phylogenetic hypotheses using different types of data? And then how do you interpret phylogenetic hypotheses or trees? Okay, so in this reading guide, I'm going to do a little bit of talking about strategy for reading papers. So first of all, you can skim the abstract to get an idea of what the paper is going to be about. That's usually how I find papers, skim some abstracts. And if it looks good, then I'll go through and I'll start looking at figures. So that's what you're going to do. You're going to go right away and start looking for figures. Okay, figure 1. This is just a map of sampling locations. Looks pretty typical. Does anything stand out here? Not so much. Most of the islands have at least been sampled by one or more sites.
Look, Mommy.
Hi, honey. You've got lots of colors on you. Okay, figure 2 and figure 3 are related, and these are basically terminology for you on the osteology. So you don't need to know this terminology, but you're probably going to have to refer back to here a few times as she defines characters. And I've highlighted some of the characters that she uses. So figures 2 and figure 3, a couple of things highlighted. Figures 4 and 5 go together. Figure 4 shows how exactly she quantified the curvature of the bill. How repeatable do you think this type of a measure would be if different researchers used it and on different specimens of the same species? How does this compare to the traits that you guys used on owls and to the types of traits you thought would be most useful in developing morphological phylogeny? And then here she's plotted that degree of arc, and I think this is for all of her taxa. Okay, so now this is kind of fun. What she does is she goes through and does some comparisons. So she takes some measurements and then she plots them just for drepanidines, those are Hawaiian honeycreepers, that have finch bills versus all of those honeycreepers, and then compares them with finch bills that are not honeycreepers, so outgroups, the carduline finches and the emberizids and so on, and then all of the outgroup taxa. So what is the pattern here in terms of the amount of variation and where it's centered on within honeycreepers, and then also just the finch bills, and then for the outgroups. Then she does this a few times as she goes through, right? So here's another figure 7 is similar. Is this right in terms of what she's showing you? Is this showing a same or different pattern? And then she shows you another type of measurement in figure 8, and then, you know, within honeycreepers, dreps, and just the outgroups. This is the angle of the ramus to the symphysis, and so I went back and looked at, you know, figures 2 and 3 to find what's the ramus, what's the symphysis, and actually she tells you in here as well. Okay, it's going to start getting good now. You know, a few more of these kinds of things. Here's another description of how she identified traits. Pretty soon we're going to get into something good. So I'm kind of skipping over some of those. I'm not too concerned about them. But here we go into the tree, and actually there's a table first. This table has the informative characters, and that means characters, you know what informative means, right? They had states that were not all unique to a single individual. That is, they weren't autapomorphies. They're synapomorphies, so they group different species. So how many informative characters were there in the different matrices? And she'll tell you later about the matrices, but basically she has divided the taxa into 3 different groups based largely on the completeness of those skeletons that she has to work from. Okay, and then the legend actually for figure 13 is here on this page right here, and so she tells you that you know, the consistency index for this tree, which is nice, and that it's a consensus tree. She also tells you that asterisk or different symbols mean that species are extinct or might be extinct, and if they are only known from fossils or if they're also known from historical specimens, so specimens collected from the 1700s and on. So you can see the honey creepers are here. You want to take a quick look at this phylogeny. This is, of course, exciting. You read the legend first and figured out what the symbols meant. So compare this with what you know from the molecular tree. And this, of course, is a little bit difficult, right? Let's see if I can find this. I put together a couple of notes here for you. One thing to note is that there are a lot of birds on this tree that have these symbols on the left within the honey creepers, and that is because most of the Hawaiian honey creepers that once existed are extinct now. So you can see over time in red, this is the decline of Hawaiian honey creepers. So before Polynesians arrived, there were about 56 species. After Polynesians arrived, but right as Europeans made first contact, there were 33 species, and then there are actually probably about 17 still alive today. So kind of a bleak process there for the Hawaiian honey creepers. But here's the difficulty with that tree is that she has everything written out as scientific name, and I didn't do that with my paper. I thought that wasn't really particularly helpful, and especially because the genus names have changed a lot for honey creepers, so it's really hard to keep them straight. So what I did in this picture here is I'll zoom in. I put the pictures from my paper on, and I'll post this PowerPoint slide for you so that you can see that, but you're probably going to need to write all over here with some of the species that are in my paper so that you can compare a little bit better, right? So let's go back now. Okay, so a couple of questions you're going to want to answer here. First things you're going to look at are, okay, are the honey creepers a monophyletic group? What are they sister to? Is that the same as in the molecular paper? And of course you're going to annotate like crazy. Okay, let's keep going quickly here through some more figures. Table 2, this is how they test alternative hypotheses. So what they're going to do is, lots of people have written about the Hawaiian honey creepers. You'll see that as you read the paper. And so a lot of hypotheses have been put out there. And so she's going to test with her data how likely these different hypotheses are. For the most part, you don't need to really worry about these. These are basically in this table. How likely is it that some of these crazy fossil forms are honey creepers or drapanidines? And so 1 through 11 are based on that. And we're not going to focus on that for our reading of this paper. But 12, she wants to know if the honey creepers and the cardiolines are sister taxa rather than honey creepers are nested within cardiolines. And so she takes a look to see if you were to force the relationship of being sister rather than nested within, how many additional steps, how much longer would that tree have to be? And basically 3 additional steps, so not particularly long. And so then she also looks at the support that honey creepers are more closely related to cardiolines than to emberized finches, and that's a few more steps, 12 steps. So you want to also go back then and look at that figure and see, well, how many nodes would need to be different? How many nodes would you have to collapse? That's something that we've done for other, when we're looking at other hypotheses. Okay, then we're going to go a little deeper in just to the Hawaiian honey creepers, and here I've highlighted the species that are extant, so species that are in my phylogeny. I think I didn't quite get them all, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are a couple extra that I didn't get fully highlighted on here, but you'll want to do the same thing and note which species are which. So she's got some abbreviations here. This must be Palila. There's a Kepa down here, Hawaii creeper here, probably Akiapola'au, Hawaii Amakihi, Iivi, Apapane. So you just want to annotate a couple other ones so you get the idea of where things are coming out. Note that she has 11 groups set out here and also in the next tree. Oh, and then she's going to show you here these figures, and there are species numbered 1 through 11 to show you what type of skull morphology is present in those different clades. It'd be nice to see these skulls right next to the clades on the tree, I think. Again, here's another testing alternative hypotheses. We get into things like the tubular tongue, which is a great trait found within the honeycreepers. And then here's another similar looking tree. I think it has more taxa in it than the last one we looked at, but it still has those same 11 clades. And I think we're done with figures for now. So then we go back up. Now we're done looking at figures, we can start to read the paper. So as you read, you want to define words you don't know. I already told you what osteology is if you didn't know. 9 primaried oscines are a group of songbirds that have 9 easily visible primaries, and they have a 10th reduced one. This is actually a pretty well-defined group, or it has been. I haven't checked in the most recent phylogeny that came out in December if that's still a good group or not, but it includes warblers, blackbirds, buntings, tanagers, grosbeaks, longspurs, snow buntings, and fringillid finches. So here are a couple of pictures. This is from the Tree of Life project. Okay, so back to your paper. I double-checked quaternary. That's the time period that began 1.8 million years ago, includes the Holocene and Pleistocene. She'll talk about that. And then I looked up Rhamphotheca, which is the sheet of keratin that covers the bill. It's not the bone of the bill, but the sheet of keratin. So she'll talk about that in a little bit. So just look up the terms that you don't know, keep track of those. An introduction is going to tell you stuff that you largely know already, right? That honeycreepers have really faced a lot of horrible extinction. But she's also going to state her objectives. These are going to be important for your message box. She's got a few of them here, and then also she's talking about the idea of are honeycreepers related to finches or neotropical honeycreepers. I don't want you to spend a lot of time on this particular part about finches versus neotropical honeycreepers. You could make a short list just to see what are the types of traits that suggest a relationship with finches versus honeycreepers, but don't spend a lot of time on that. She's going to talk about the idea of melanodreps and chlorodreps. I actually colored this on her phylogeny for you, so you could